This week, we are dealing with solution of Laplace's equation. And so far, we have considered the solution in 2 dimensions. And we found how to use separation of variables in Cartesian and polar coordinates. In this lecture, I want to go to spherical coordinates, and to keep the problem 2-dimensional, we will consider azimuthal symmetry in the problem. So, this week is today's lecture is on use of spherical coordinates. That is r, theta and phi in problems with azimuthal symmetry. That means no phi dependence, so that the problem remains 2-dimensional. So, in spherical coordinates, the Laplacian del square is given as 1 over r square partial with respect to r square partial with respect to r, plus 1 over r square sin theta partial with respect to theta, sin theta partial with respect to theta, plus 1 over r square sin square theta double derivative with respect to phi square. And we are considering azimuthal symmetry. And this implies no phi dependence, and therefore, del square operator that we will be considering will be only the r and theta terms. So, this is what we are considering now in this lecture. Again, we are going to use separation of variables and take the solution V r theta for the equation del square V r theta 0. So, we take V r theta, V r and theta to be equal to some function r of r and some function p of theta. And when I substitute this in the Laplace's equation, what I get is 1 over r square d by dr acting on r square dr derivative, and there is going to be p theta outside, on which this r operator does not work, plus 1 over r square sin theta d by d theta of sin theta dp by d theta times r is equal to 0. I can take away this r square and divide by r and p, and then I get 1 over r, r square, r double prime plus 2r, r prime plus 1 over p, 1 over sine theta d by d theta of sine theta dp by d theta or p prime is equal to 0. So, when I use separation of variables, this is the form that this equation gets reduced to. So, just to recap, when I am writing del square V r theta equals 0 and taking V r theta to be some function of r times a function of theta, the equation I get is 1 over r d by dr of r square d r by dr plus 1 over p 1 over sine theta d by d theta of sine theta dp by d theta equals 0. And using the standard methods of separation of variables, I am going to write this as 1 over r. Let me write this in the other form, r double prime r square plus 2r r prime is equal to minus 1 over p 1 over sine theta d by d theta of sine theta p prime, where r prime is dr by dr, p prime is dp theta by d theta. On the other hand, I am going to reserve p prime for something else. So, let me write this as dp d theta right now. And now, the left hand side is a function of r only, the right hand side is a function of theta only, and therefore, both of them should be equal to a constant. So, what I am going to have is that 1 over r square r double prime plus 2r r prime is equal to some constant, and 1 over p 1 over sine theta d by d theta sine theta dp d theta equals minus this constant. Let me make a change of variable and use cosine theta as variable x, because cosine theta is natural in spherical polar coordinates. And therefore, this equation can be written as one over sine theta d theta will become, so 1 over p is there, d by d cosine of theta with a minus sign in front. Inside I am going to write sine square theta dp d cos theta, again with a minus sign here, and this would equal to minus this constant. Replacing cos theta by x, I get d by dx 1 minus x square, that's sine square theta, dp by dx minus this constant times p is equal to 0. That's the equation for p. Let us see what does it expand to. So, I got d by dx of 1 minus x square dp by dx minus this constant times p equals 0, or 1 minus x square p double prime minus 2x p prime minus this constant times p is equal to 0. I need to solve this. So, I have p x, which should be number 1, well behaved. That means single valued, finite, and continuous. In the interval mod x less than or equal to 1, which basically implies that cosine theta has this range minus 1 to 1. So, it is well behaved in this entire range, and therefore, it is well defined at mod x equals 1 also. The endpoints are included. So, this has to do that. As you know that this is an eigenvalue problem with proper boundary conditions and all that, and you do series solution, then you get this constant that I am writing to be equal to minus L plus 1, then only the series terminates, and the equation then becomes p double prime 1 minus x square minus 2x p prime plus L plus 1 p x equals 0. This is a well known Legendre polynomial equation, and the solutions are p L x. That part I need not go over. And for each p L x, I have p L x is a polynomial of degree L. They are well behaved at the ends, and 2 p L x is even bracket odd if L is even or odd. So, p 0 is going to be an even function. In fact, p 0 is 1. p 1 is going to be an odd function. p 1 x is actually x, and so on. Number 3, they are not normalized, but they satisfy orthogonal property, and that is, if I integrate from minus 1 to 1, p m x p n x dx, it comes out to be equal to 2 over 2 m plus 1 delta m n. So, they are orthogonal. They are not normalized. And as I said earlier, p L at 1 is 1. So, these are some of the properties. Then they also satisfy certain recursion relations, which we will keep using in the problems as they come along, but I will request you to go over this in any mathematical physics book or Jackson itself. So, this is your homework for this. Now, let's look at the R solution, because we have already found that when I write V r theta as R r, P theta are Legendre polynomials. So, the corresponding R equation then becomes 1 over R d by dr of R square dr by dr equals L plus 1. So, let me just warn you here, I may have missed a minus sign along the way. Please correct it. So, the equation that you get is R square R double prime plus 2R R prime minus L plus 1 R equals 0. The solution that we look for is of the form R equals R raised to lambda, and you get lambda plus 1 minus L plus 1 equals 0, and therefore, lambda equals either L or minus L plus 1. Therefore, for a given L, the solution is A R raised to L plus B L over R raised to L plus 1 times, let me write it A L, P L cosine of theta. So, let me just recap. We are solving this equation del square V r theta equals 0, taking V r theta to be a product function R P theta. I get the solution to be one particular solution for given L, A L R raised to L plus B L over R raised to L plus 1 P L cosine of theta. In general, a solution is going to be a linear combination of this, and therefore, I can write that in general V r theta is going to be summation of L equals 0 to infinity A L R raised to L plus B L over R raised to L plus 1 P L cosine theta. And this is the solution for systems with azimuthal symmetry. I can expand this. Now, ALs and BLs are going to be determined by the boundary condition. And that is where the art is, how to apply those boundary conditions. That's one way of solving. Let us see what the solution is on the z-axis. So, what form does this solution take on the z-axis? On the z-axis, theta is equal to 0, which implies cosine theta is equal to 1, and therefore, P L cosine of theta is 1. All Legendre polynomials have this value 1 at 1, and therefore, in azimuthal symmetric problem, V on Z is going to be equal to summation L equals 0 to infinity A L Z raised to L plus B L over z raised to L plus 1, where ALs and BLs can now be determined from the problem. So, this is another way of solving the problem. If I can somehow generate the solution on the z axis, then I can write the entire solutions. Once I determine AL and BLs, then I can write the general solution by including PL cosine theta out here. So, either through boundary conditions or through comparison with the solution on the z axis in the known cases, you can figure out the solution in these kind of problems. Let me take one example of this. Charge Q, it's a point charge, is on the z axis at a distance d from the origin. Right. The corresponding potential in terms of Legendre polynomials. This is one problem where I'll make use of the solution on the z axis and then use that to write the general solution. So, let us see, I've been given that there is this charge sitting on the z axis at a distance d. So, V on z is going to be 1 over 4 pi epsilon 0 q over modulus z minus d. There are very clear two regions of interest. One is z greater than d. In that case, the solution becomes 1 over 4 pi epsilon 0 q over z minus d, which is equal to q over 4 pi epsilon 0 z 1 over 1 minus d over z. Keep in mind that d over z is less than 1. And therefore, I can write this solution as equal to q over 4 pi epsilon 0 1 over z 1 plus d over z plus d square over z square and so on, which is equal to q over 4 pi epsilon 0 summation L equals 0 to infinity d raised to L over z raised to L plus 1, and this converges. Now, compare with Vz equals summation L AL z raised to L plus BL over z raised to L plus 1. This immediately tells you that for z greater than d, ALs are 0 and BLs are q over 4 pi epsilon 0 d raised to L. So, we have gotten BLs for this problem. Let us go for z less than d. If I go for z less than d, then Vz is equal to q over 4 pi epsilon 0 1 over d minus z. And this time I take d out and write this as q over 4 pi epsilon 0 d 1 over 1 minus z over d. Z over d is less than 1, and therefore, this is q over 4 pi epsilon 0 summation L going from 0 to infinity z raised to L over d raised to L plus 1. And this immediately gives you that AL is q over 4 pi epsilon 0 d raised to L plus 1, and BLs are 0 for z less than d. And therefore, the general solution V r theta is going to be equal to q over 4 pi epsilon 0 summation L equals 0 to infinity r raised to L over d raised to L plus 1 P L cosine of theta for r less than d, and it is going to be equal to q over 4 pi epsilon 0 summation L equals 0 to infinity d raised to L over z raised to L plus, not z, r raised to L plus 1 P L cosine of theta for r greater than d. These are your answers. This also gives you the generating function for PLs, which in maths books it's given beforehand, but we are now getting it through our physics and electrostatics by expanding the potential for a point charge. So this relationship is 1 minus 2 x t plus t square raised to minus a half is equal to summation n p n x t raised to n. And I'll leave this for you to prove this. Finally, I'd like you to solve this problem using the method just described, that is, writing the potential on the z-axis calculate the electrostatic potential for a ring of radius r kept in the xy plane with its center at the origin. The ring carries a charge Q. So again, what you will do in this is take this ring, write the solution on the z-axis, and then taking hint from there, determine ALs and BLs, and then write your general solution for any r and theta. So let me now conclude this lecture by stating that we solved Laplace's equation using spherical polar coordinates for systems with azimuthal symmetry. And in this, what we found is that the solution can be written in terms of Legendre polynomials and powers of R as AL r raised to L plus BL over r raised to L plus 1, PL cosine theta, and ALs and BLs are determined from boundary conditions, and also from comparison with solution on the z-axis. Thank you.